Hi everyone, welcome back to the channel. I'm Manisha. So today in this video we are going to discuss one research paper which is recently published. The name of the paper is CAN, Kolmogorov-Arnold Networks. In this paper they compared the CAN method with a multi-layer perceptron neural networks. So I found it interesting. So let's see what we have in this paper. So before we enter into the paper details, we will see the title, author of the paper. So the title is CAN, Kolmogorov-Arnold Network. This research paper is related to a specific type of neural network, or we can say mathematical model, and the author of this paper are from institutes such as MIT, California Institute of Technology, Northeastern University, and the NSF Institute of AI and Foundational Interactions. I also left the reference of the paper here. So in this paper what I noticed that there is a method comparison mainly with a multi-layer perceptron. So I thought of including some basic things about NLP. So NLP is a type of neural network, as we know, and it is specially designed for regression classification task. It can also used for feature selection. So we can take an example like making prediction. If it is a regression, classifying something, if it is a classification. So it has three main layers: input, hidden, and output layers. Hidden layer can be multiple layer. This is the basic structure about NLP. There are other things also like activation function, then weights between nodes, and then some parameter tuning like a training of the model. I have created a separate video on NLP. You can check it out later. So after this we will jump into the paper. So this figure is from the paper. It's a MLP based diagram. The slide shows these model shallow diagram and model deep diagram. So what it exactly is, it's a representation of multi-layer perceptron which consists of layers of nodes. Nodes can be called as neurons, and they are connected by edges. Each edge has a learnable weight and each node applies a fixed activation function. So here is a learnable weights on the edges and the fixed activation functions that we see on the nodes. Moving to the next is a universal approximation theorem. So this theorem states that the NLPs can approximate any continuous function given enough neurons in the hidden layers. Talking about the formulas that we have, shallow and the deep formula. So the shallow one represent a single hidden layer in NLP, and the deep formula that we see, it shows the composition of multiple layers in the NLP. Now we will see the approach which is CAN. It is a novel approach published 2 weeks before, and the aim of this video is to explain the approach. So what is CAN? It is an alternative to multi-layer perceptron. It uses a fixed activation functions on their nodes. This figure is from the paper. So the first thing that we can see is a Kolmogorov-Arnold representation theorem. So this theorem states that any continuous function can be represented through a combination of simpler and continuous functions. And next is the formula. It shows that how complex function can be decomposed into series of operation. Moving on, a structure of the network, diagram B displays the structure of CAN where each edge has a learnable activation function and each node performs a summation of its input. Diagram D breaks down the network into three layers where each layer processes the outputs of the previous layer through nonlinear learnable function. And a CAN equation describes how an input X is transformed sequentially by three layers, with each layer applying a specific transformation and passing the result to the next level or layer. Now we will see a bit more about a CAN. So CAN name is defined from these three. Scientist Kolmogorov and scientist Arnold, they worked on theories on function representation, and network is from neural network, and that's how the CAN is defined. In here the paper highlights three things: mathematical, accurate, and interpretable. These are the three key strengths of the CAN. Also the study compared CAN with a traditional multi-layer perceptron and NLP, and CAN shows a good performance and efficiency in parameter use. Also, according to the study, CAN are not just theoretical robust but also highly effective in practical implementation. Now we will see another diagram from the paper. So the diagram here on the left hand side shows a neural network where b-spline functions are used as activation functions. On the right hand side of the figure shows how a single b-spline activation function, which is represented as a phi of x, is decomposed of a weighted sum of basis splines. The coefficient Ci determines the shape of b-spline, which can be adjusted to adapt to more detailed data representation by increasing number of nodes and basis functions. And this adaptability allows for a more precise modeling in the neural networks. Now moving on to the next, that this slide shows how increasing grid size in the CAN improves their ability to accurately model a complex mathematical function. So here grid size is from 3 to 1000, and additionally we can say that this graph shows a pattern of sharp drops in error when a grid size is increased. So here you can see. Moving to the next slide. So this slide outlines a systematic process of symbolic regression using CAN. We will see all of these steps in detail. So starting with the step 1, which is a train with a sparsification. So the network starts by training on the data while applying sparsification techniques to ensure the model focuses on the most relevant features, reducing the complexity and enhancing interpretability. The next step is a pruning. So after initial training, the model is pruned, which involves removing less significant connections or nodes, and it simplifies the network further without losing critical or key information. Next is a set specific functions. So there are three steps, 3a, 3b and 3c. So in 3a, nodes are set to represent a specific function such as a sign, and in 3b, other nodes may be set to represent other mathematical operations such as squaring the input, and the next is the more additional nodes might be configured to represent exponential functions. So next, step number 4 is a train affine parameters. This training is done fine-tune the affine parameters, which can be constant or coefficient within a symbolic expression identified in the previous steps. The next step is the output symbolic formula. The network then outputs the symbolic formula, provides a mathematical representation of the data relationship it has learned. And the next step is a number snap. So this is applied to the output formula to adjust numeric values to more standardized and meaningful figures. So this all process is effectively translates a complex data into concise and symbolic mathematical expression through this number of steps. Now next we saw that one of the key factors of CAN is accuracy. In this slide we will see what is that. Here it's a fitting symbolic formula. This provides a comprehensive analysis between CAN and MLP across 5 different mathematical functions. So first is the function types that we see in this figure is the comparison between several types of functions. We also see the depth variation. So both CAN and MLP are analyzed at various depths. It started from 2 to 5. And there is another thing that is about a performance matrix. So the test root mean squared error is plotted against the number of parameters in a logarithmic scale. So lower RMSE values indicate the better accuracy. If we compare the results, then we see that the CAN generally show a steeper decline in root mean squared error with a fewer parameters compared to NLP, which indicates that CAN require fewer parameters to achieve similar or better accuracy. It's about again accuracy, continual learning performance. In here you will see a toy continual learning scenario where the model sequentially learns data around each of 5 Gaussian peaks. The top row shows the original data for each phase, And then if we in terms of model comparison, we see that the can adapt to the new data without forgetting previous patterns. So I highlighted here indicates that the effective continual learning and memory retention. So in contrast, NLP includes a catastrophic forgetting, so where they fail to retain earlier learned patterns as a new data is introduced. So that's why CAN are potentially more suitable for tasks requiring robust continual learning and adaptation compared to traditional NLP. Now next is about CAN's interpretability. So in here you will see different different arithmetic operations, multiplication, then division we have, and then numerical to category, deeper composition, phase transition, and special function. So in conclusion, I can say that CAN is not only capable of handling basic or complex mathematical operations, but also shows their interpretability in various computational tasks. So for example, the first one, multiplication, I can say that the CAN shows structure for computing the product of two inputs, that is x and y, and the network combines this input and produce an output that is x into y, which shows that the CAN has a capability to perform on basic arithmetic operations. So the next is about, should I use CAN or NLP? So the slide here presents a decision making framework to determine whether we should use CAN or NLP based on various criteria. So these criteria, first criteria is accuracy, and in accuracy you see three different things. First is compositional structure. If your problem requires a modeling compositional structure, go with a CAN. If the second is a complicated functions. If problems involve complicated function, prefer CAN. Continual learning, if the CAN is recommended if your task involves continual learning. The second key part is interpretability. In that, first is the dimension. So if dealing with high dimensional data, CAN is recommended. And then next is a level. So for tasks where interpretability is a priority, so go for the CAN. Then the last parameter is efficiency. Here the first thing is want small model. So if the goal is to minimize model size, CAN is recommended as they can be more parameter efficient. And second one is want fast training. So for this scenario, when the fast training is important, NLP might be a better choice, not the CAN. As they are typically less complex to train compared to CAN, so which might require more setups for a training. So this framework actually helps us in selecting appropriate method or network. Either we should go with a CAN or NLP. That's all more or less for this video. Thanks for watching the video. So I hope you like this video. If you like this video, please subscribe to the channel, and I will also leave the link of the paper in the description box. If you have any question, please leave them for me in the comment box, and take care and see you in the next.